So we'll continue from last time and talk about inductance. There are plenty more videos on the study desk that builds from those basic concepts, and we'll talk about them on Wednesday. So for now, we'll continue with the definition of inductance. And the idea was that whenever there is current, you would have magnetic flux. And we know that, not that we can see the flux, we know that by the effect that the flux would have on certain things. For instance, an example would be a compass. So if there's a magnetic field, it will have an effect on that compass. That magnetic field would be either strong or weak, and you can tell by doing a little test. So you can say, oh, at this point in space, in three-dimensional space, magnetic field is strong there, so it means the flux density is strong there, and you can tell that. The idea that flux density represents a vector field is important. It's not a scalar field, it's a vector field. And it is vector because it's got a magnitude, which is a strength, if you like, and it's got a direction. Up to now, we have more or less explained the idea of flux density and the fact, again, that it's got magnitude and direction. But a lot of times, we are going to deal with not flux density, but a certain amount of flux. And when you go from density to an amount, you usually, well, all the time, you multiply by something. Like I say, if you know the density of iron, and you want to find a quantity that is a quantity of mass, then you would take density and you multiply by volume. In other instances, you could be taking density and you will be multiplying by area. And in this particular case, flux density times area gives you amount of flux. In other instances, you in fact take density and you multiply by a length, because that density is given per unit length. I don't know if you've ever heard of that, but if you do power systems analysis, you would see that we talk about a line of charge, and we talk about a density in the form of Coulomb per meter. So if it's Coulomb per meter and you wanted to know the amount of charge, then you would multiply Coulomb per meter by length. On the other hand, you could have Coulomb per unit volume, the so-called volumetric charge density. Then you will multiply by volume. On the other hand, you could have a surface charge density. In this case, you will multiply by area. Or a linear charge density, in which case you will multiply by length. So flux density is it's like a surface. It relates to a surface. So if you want amount of flux, you would take density and you would multiply by an area. But I thought I ended the lecture the other day and I said, oh, be careful about this multiplication, because it's not an ordinary multiplication. You're dealing with a vector here. Flux density is a vector. And if you're going to multiply by area, you have to do so very carefully. Like if I were to say, this is the area, this is a 3D diagram. So that's a 3D diagram, which I'm not very good at drawing. But let's say you had a flux density going like that. So that's B. And we put a bar underneath to represent a vector. So flux density is a vector. Now this is the area. Now you're looking at the flux crossing that area perpendicularly. So that's the amount of flux. The flux has to cross the area perpendicularly. So if you were to take an area, say, like this one here, and you say, I want to know how much flux is going through, you can't just take B times A. It would be wrong. You have to look at the area, and you have to look at the flux density. If the flux density was going that way, you will get maximum amount of flux crossing the area. That will give you maximum amount of flux. On the other hand, if the flux density vector was this way, then you're not going to have as much flux associated with that area. If the flux density was like that, then there's plenty of flux density, but the amount of flux is actually 0 for this area. So you have to be careful. Therefore, instead of doing an ordinary multiplication, you actually do a dot product. Remember, the result of a dot product is a scalar. And that makes sense because the amount of flux is a scalar. A cross product is different. With a cross product, the result is a vector. And we do use cross product in other instances, but I'm not going to look at that now. Let's look at this idea of amount of flux. Now, when you do a dot product, you do so with two vectors. Like you could have vector A and vector B, and you say A dot B. But here, flux density is a vector. That's okay. But we are multiplying by an area. So the question is area a vector? And we have to make it a vector, because otherwise we can't do the dot product. So this is another thing that you have to understand, is that area is actually a vector. Or if you look at a little bit of area, it's a vector that we could call A, vector A. And the direction of the vector representing area is normal to that area. Right? So if I come back to this, and I say, oh, that's an area. So that area is represented by a vector that is perpendicular to it, normal to it. Right? So you have to understand that. Which means then you get maximum flux if the flux density is at right angles to that area. So we say amount of flux through an area A, which we are assuming is flat here. I'll come to areas that are not flat in a minute. So if an area A assumed flat is equal to B dot A. If I want to do this correctly, I'll have to put an n there, where the n is unit vector normal to the area. And that's equal to BA, B times A, if equal to them, if B is constant and normal to normal to n. Normal means at right angles. So amount of flux is equal to BA, like flux density times area, only if those conditions are met. That is, only if the flux density is constant over the area, and also only if the flux density is normal to that area. If those conditions are not met, then you have a different formula, a more complicated formula for amount of flux, which we don't need in this course. But I still want your mind to be open enough to realize that amount of flux equal to B times A is only true if those conditions are met. And I am hoping that you would think, oh, what would happen if those conditions are not met? If those conditions are not met, you would find, in general, whenever those types of conditions are not met, then something quite interesting appears. What happens to multiplication, like pure multiplication, when things are not constant? For example, distance is equal to speed. Yeah, that's under special conditions. But let us say a distance. I'll say distance. Distance is equal to speed times time. So this is a multiplication. But that's only is true if during that time the speed was constant. So what happens to multiplication when this is not constant? What happens to multiplication? You know the answer. It still can be linear. Yeah, linear has got a special meaning. What happens to multiplication? As I say, you know the answer. I hope you haven't wasted your time. So what happens to multiplication if the speed is not constant? You can still say distance, but you would say d distance. A small change in the distance is equal to speed, which is a function of time now, times a small change of time, which people call dt. And what do you do with that to get distance now? So you say distance equals have you seen that before? Yeah, so you would integrate. And that's what the kind of message that I want people to have, because you spent a lot of your time doing mathematics and you've done those integrals, but what does it mean? It means it's very useful whenever something is not a constant. So this is not a constant now. So if you want to calculate the distance you've covered, you do an integration. And what is an integration? An integration, don't let anyone tell you that it's complicated. It's not. An integration is a sum of products. So that means sum. And this is a product. And you're taking little bits of products. You're adding up, say, from 0 to t. So you're saying, in the first instance, at time 0, my speed is so much, I'm covering a little bit of distance. And then a little bit of time later, you have another speed, but that's fine. You can still calculate the other incremental distance. And you add them all up. And adding them all up to give you all that distance is just that integration. So an integration is a sum of little products, of incremental products. So a multiplication, a bulk, that's a bulk multiplication over the whole time, becomes an integration if you can't do the bulk multiplication, because this is changing with time. So you are doing a little bit and a little bit and a little bit, and then add them all up. So what do you think will happen to this multiplication to get amount of flux? It will become an integration. So amount of flux is actually integral of B dot dA. That allows for the fact that the flux density is different in different incremental area. So you basically calculating it for a little bit of area and then add that to another amount of flux related to another bit of area and so on, and that gives you the integration. Integration is summation. I mean, the word integrate means you're putting together. So it's a summation. So as I say, why did you learn mathematics? You learn mathematics so that you can translate it into those practical situations. So remember then, while I'm saying flux density equal to, amount of flux equal to flux density times area, I am saying those that with quotient, two things to remember is that normally you would do this as a dot product, not as a normal product. And secondly, if flux density was different in different places on that area, then you would have to do an integration and not a straight multiplication. Okay, so the reason I say this to you is I am supposed to teach at university level, right? I used to teach in high school, way back. And when I taught in high school, I stopped there. It would be irresponsible for me to stop here because I'm teaching at university level. I have to get you to that sort of thing. And that's what I'm doing. Okay. So we know what flux density is. We know what amount of flux is. And we don't have to calculate the amount of flux today. We just have to understand that there's such a thing as amount of flux. And if I wanted to know how much flux comes out of a magnet, like this one, then I can just integrate the flux density over that area, and that will give me the amount of flux coming out of that magnet. However, in this course, we are not interested in flux coming out of a magnet, but we are certainly interested in amount of flux coming out of coils. But it's the same thing. If you had something quite easy, like something like this, say you built a magnet for whatever reason, you built a magnet that looks like this, then you can say, okay, there is a certain amount of flux that comes through there and around. And if I want to know the amount of flux that links this coil, then I can look at the flux density and integrate over that area. I can assume that that's all the flux. Of course, in practice, there would be some flux going like this. If I wanted to be serious, I would integrate over that whole area, get that amount of flux, and that amount of flux would be the flux associated with the current going in that coil. And people have defined, I would say people would have made the assumption initially that amount of flux is proportional to current. So there's current going in this coil, so amount of flux is proportional to current, as I say. Not only that, but you would also quite logically say that the amount of flux would be proportional not just to the current, but to the number of turns in this coil. So you would make that assumption, as I say, and you can test it. If you wanted to test it, you will be able to. You could come up with an experiment to test that. And I would say if you were to go back 500 years ago, that's exactly what people would have done. They would have doubled the current and see what sort of effect they would have here, measure that with a compass or whatever you use to look at the flux density there, and they would have found that if they double the current, they get double the force, say. And that would have told them that there's a constant of proportionality that relates amount of flux and the product of current and number of turns. So people would have found so if I go to there, look, the red shows, doesn't matter, just do that in black there. It shows on the screen. Oh, good, okay. So people would have found that amount of flux observed that amount of flux is proportional to the product of current I and number of turns N. That is number of amount of flux here, so amount of okay. That is okay. So I will put current there. So what I say there is right. Amount of flux is proportional. Yeah, good. Now, what we call that's I there, and the amount of flux is there. So it's phi for amount of flux. So amount of flux in this one, it's a straight line. But there's another graph that I'm interested in that I'll draw for you very soon. This statement is true. There's no problems with it. The amount of flux will be proportional to the product Ni, but you'd still get a straight line if you plot just against I. So that's still okay, because number of turns is a constant. Okay, so I'll rub this off and put another graph there, which really is the one that we are after. So I'll rub that off. There is something that people define as flux linkage. So if it is assumed that all flux lines link all turns in a coil, then flux linkage is n times phi. So that's a term that people use. And the reason for that is if you look at an area, for example, if you look at this area, and you had only one turn there, say one turn of wire going on the edge of that area, then that turn of wire would have a certain inductance. Now, if I put two turns of wire, so I go two turns and same area, then I expect the inductance to, which we'll define very soon, I expect the inductance to double because you got double the effect. You can double the effect either by doubling the current or you can double the number of turns. So that's why people have defined that. Now, that is only true, this idea of flux linkage is only true if all the flux link all the turn, which in situations that we are looking at, like in transformers, that's almost true. On the other hand, if you come back to reality, then the flux linkage is actually a bit less than this, because there will be some flux that link only some of the turns and not all of them. But we are not going to worry about that today. So this is a bit of an assumption, and you can make it as true as, you can force it to be true by using iron like this. If you have iron, then the flux tend to link all the turns. If you don't use iron, if that is in air, then you will have some flux, a big proportion of the flux leaking out and linking only part of those turns rather than linking all of the turns. So here we are assuming all the flux link all the turns. Now if you do that, then just like we had that graph before of phi against I, you can plot a graph of n phi against I, and that graph will also be a straight line, because all you've done is phi against I is a straight line. N phi against I will also be a straight line because n is a constant. So the gradient of that graph is what we call inductance. So that's inductance. Gradient equals inductance. In other words, inductance is a constant of proportionality. And as said before, you will find that this is generally true for things. Resistance is a constant of proportionality. Capacitance is a constant of proportionality. Inductance is also a constant of proportionality. That is, they have been defined for convenience, because people have observed that flux linkage is proportional to current. Instead of say that all the time, they say, oh, well, since it's proportional, let us define something called inductance, which is the constant of proportionality. Similarly with V equal to IR, I mean, people did not know that V equal to IR, but they observed that for some things, voltage was proportional to the current that goes through, voltage across proportional to current going through. So they saw that and saw that and saw that and say, oh, it's proportional. So then let's give a name to that constant of proportionality. Let's call it resistance. So it's similar with inductance. Of course, just like resistance depends on physical dimensions and material properties, this is also what you will find in engineering. In engineering, a lot of things depend on dimensions and material properties. So just like resistance depends on dimension, like R equal to rho L on A. So L on A is dimensions, and rho is a material property. rho being the resistivity. Similarly, a lot of things in life depends on dimensions and material property. Like, say, the weight of bone matter in your body depends on dimensions of those bones and depends on the material property of that bone being the density of the bone. So the idea of things depending on material property and dimension is not at all surprising. So this inductance here, it will depend on dimensions, physical dimensions, and material property. If you want to know which material property, that will be for another course and another lecture. But for now, we'll just stick to inductance. If you look at the video on transformers, which is in fact on your study desk, you will know what the property is. But I won't say it now, otherwise I'll be going too far. But you watch the video and you will see what material property inductance relies on and what dimensions it relies on. Okay, so that is inductance, and we would now look at this further. So this is, again, flux linkage there, and we'll write that equation down. As I said with those things, whether it's capacitance, resistance, inductance, current source, voltage source, with all of them, you could show the relationship as a graph, or you could show it as an equation. Sooner or later, you will have to write the equation, because without the equation, you can't take things further and do calculations. So that has to be now expressed as an equation. So let's do that. So what we will say is, whilst I was doing this, of course, when we did resistance, if you remember, we showed the straight line as a gradient. And then we say, oh, well, this is not 100% true. There are situations where that straight line becomes nonlinear, becomes a curve. And we gave an example. And the example we gave was the surge diverter, or the MOV. Similarly here with inductance, it's a straight line, yes, for cases where you keep getting more and more flux as you push more and more current. And that is sort of true, especially if you're pushing flux in air. And I understand that people have pushed flux enough now to get about 4 Tesla in flux density. I don't know if there's more, if people have done more, but around 4 Tesla is seen as a really good, strong flux density. That's if you can keep pushing current and getting more and more flux. In air, in theory, you can do that, but in iron, you can't. There will be a point where, as you push more current in the coil, push more current, the proportionality doesn't continue. That is, you don't keep getting more and more and more flux. There will be a point where the iron would saturate. At that point, pushing more current doesn't mean you get more flux. Not in proportion anyway. And at that point, we say the iron is saturated. And I mention this here because that's exactly what we're going to focus on when we look at instrument transformers. You would look at your CT saturating. So a lot of people would say, oh, the CT saturates, but you can only understand what's happening with that CT, and we are going to study that in detail. You can only understand that if you understand what flux means and what flux density means, and also what this equation means, which we're going to look at now. So what we've said up to now, from the graph that was here, we are saying n phi equal to Li. That being the gradient. Now this n phi, as I say, is flux linkage, and I can leave that like that, or if you want a symbol for flux linkage, some people use lambda, so that's flux linkage again, flux linkage, which is a nice name because the phi is flux and the L is linkage. Linkage meaning link. So you have an area, if you like a loop, and it means a flux. Every line of flux is linking that loop n times, because you've got n turns. So n turns is like having 10 loops very close to each other. And you've got the flux linking all those 10 loops. So that's why it's called linkage. It's quite interesting to look at current and flux. I don't know if you've ever thought about this, but maybe you would. And what happens is the current is a circuit, and the circuit is like this, right? And the flux is also a circuit. People rarely say that, but it's also a circuit. And what makes the magic happens is that the two circuits link. So if that's one circuit, say the current circuit, and this is a flux circuit, they link like that. So that's the term linkage. So if you think about it, you would see that these red lines is a circuit, and the current is a circuit, and they link. So that's the linkage. If they don't link, then all those things that we talk about would not happen. So it's that linking that gets it to happen. So this is the word linkage, and it's there for a reason. So there's flux, and there's flux linkage. If there's flux without linkage, then there's no inductance. Okay, so let us continue. Now, from there, you get the familiar equation, and I won't put the lambda in because most people are more comfortable if we keep the phi. So I'll keep the n phi without the lambda. So Faraday, he found that he said, so from here we go to Faraday's law. And that gives us n d phi dt equal to EMF. So Faraday say EMF equal to rate of change of flux. That is, if you don't have change of flux, you're not going to have an EMF. You can't do anything about that. This is how the world has been created. This is a law of nature. So if there is flux changing with time, then there will be an EMF. EMF standing for electromotive force, which is a very old name. It means that there is a force in inverted commas that will get electrical charge to move. Motive meaning move, force meaning a force that will cause something to move, and electric means we are moving electric charges. So that's just saying if you had a rate of change of flux, then you will get an EMF. You may not get a current. You may not get a current. It all depends on whether there's a path for the current to flow. But you can easily think of, say, a coil like this with a magnet in there. When the magnet is in there, there's plenty of flux there, plenty of flux going through the coil. Of course, if the magnet is just sitting there, you will get no EMF here. But if somebody comes and pulls the magnet, we used to do that at school. Anybody has done this at school? Yeah? So you pull the magnet and you put what they used to call a galvanometer here, and you can see it kicking. So meaning that by pulling the magnet out, you've gone from a situation of plenty of flux to a situation of zero flux. Therefore, the flux has been changing, and because of the flux changing, you will get an EMF across there. As I say, you may not get a current because there may not be a circuit there, but there will be an EMF across there, and an EMF is a potential difference, which means that there's a potential for current to flow. So you can either pull it out, or you push it back in, or you can just keep doing this. And if you did, you will get an EMF across there. And indeed, that would be the easiest way of making AC voltage by doing this. But of course, you can't have a person doing that like that. So that's why we invented better ways of doing it. But you could generate a few fractions of watts by doing that. Okay, so that's what Faraday said. EMF is rate of change of flux. So you could say, if we call that EMF E or V, it really doesn't matter. You could say V equal to N or dN phi by dt. Because that's, I should say, not flux here, but rate of change of flux linkage. That's what I should be saying. So EMF is rate of change of flux linkage. A lot of people drop that, which is not right. In fact, I myself have got into trouble by dropping this because I forget. Instead of saying V equal to dN phi by dt, I say V equal to d phi by dt, which is wrong. So it has to be the rate of change of flux linkage. Now, when you do that, you get, of course, that becomes the n being a constant. Some people believe it is, so that means n d phi dt, and that's your equation there. You can write it like that if you like. So that's Faraday's law. Now, if you apply Faraday's law to this, which is our defining equation for inductance, then you get so I'll probably rewrite this on the board and follow things from there. I've got 10 minutes, so I'll try and get to the final result there. Okay, so it goes like this. So if I start there, I would have n phi equal to Li. That's by definition. So this comes from the fact that we observe the amount of flux is proportional to current. And then we go to Faraday's law. So Faraday's law gives us V equal to n d phi dt, which has to be, if you now apply that, it has to be equal to L di by dt, assuming L is constant. So that's where we got the V equal to L di dt from. I should really use lowercase because things are changing with time, so I'll make that uppercase, lowercase, just to emphasize things are changing with time. So this is the equation that we work with most of the time. And I must emphasize here that this is actually the so-called self-inductance. Later on, we'll introduce the idea of mutual inductance. We need to understand mutual inductance because when you look at distance protection a little bit later in the course, when we look at distance protection, mutual inductance play a part. And the reason mutual inductance play a part is you have one transmission line that you're trying to protect, but there is another transmission line close by. and many times they're on the same tower, and that would have an influence. So one line has an influence on the other. So there's mutual coupling between them. So we have to introduce the idea of mutual inductance. You can see that this equation is rather incomplete, because when we write this down, this flux here can come from anywhere. It doesn't have to come only from one current. There could be other currents in other coils nearby that is contributing to the flux. So in going from there, in fact, throughout this, we have made the assumption that this flux originates only from that current. But this flux can be associated with other currents flowing in other coils, which means that you have to introduce the idea of mutual inductance. And in this course, we need to understand mutual inductance, as I say. Well, first of all, in transformers, there's mutual inductance. But by making the transformer ideal, we don't have to explicitly talk about mutual inductance. But in the case of transmission line as well, one transmission line affecting another, we have to go back to this idea of mutual inductance. And we will do so. But for now, let's say we are studying a coil in isolation. It is not affected by other coils. If we do that, then we do something very similar to what we did before. We could say, let's look at the AC case. You have an AC case there with the inductance, and you look at the current. That's a voltage there. Let's call it inductor voltage. This is L. This is VL. And this is IL, say. So if you were to look at things like that, then just like we did for capacitance, you could draw the voltage. You could draw the voltage and the current, and I would probably draw which one would we make sine? We'll make it easy if we make the current sine. So, okay, so there's a current. So it's a sine curve. So the current I is a peak current. That's a peak current there. This here stands for peak, and the formula would be sine omega t. So that's a current. The voltage, because the voltage is proportional to the derivative of the current, and you can see the derivative means slope, so the slope is maximum here, maximum and positive. Make sure you can see what slope is. As I say, these diagrams, they talk to you, so you better listen to them. So maximum slope means maximum positive. Maximum positive, so that's a gradient, which is proportional to the slope. And then the slope here is 0. So your voltage then, which is proportional to the slope of the current, would follow this curve, which is a cos curve. So the voltage will be a cos curve. And you can see everything makes sense. You have here slope is 0, so you get 0 voltage. Here slope is maximum negative, so you get maximum negative there. So that will be the peak of the voltage. Peak of the voltage there. So that's a current, RIL if you like, and the voltage VL, therefore, is the peak of the voltage times cosine omega t. So the current is a sine, the voltage is a cos. So in the case of inductance, voltage leads current by 90 degrees. And you can see this happening there. And that's consistent with this equation when the differential of sine is cos. Cosine leads sine by 90 degrees. Of course, some people represent this by a phasor diagram, and you can do so if you wish. If you use the current as horizontal, you don't have to. I mean, a lot of people get so worried about this. You don't have to draw it horizontally. There's no magic about horizontal. So you could draw the current horizontal, and if you did, then the voltage would be leading by 90, so the voltage would be there. But as I say, it doesn't have to be horizontal. As long as this angle is a right angle, that could be anywhere, as long as you keep this 90. Okay, so this is the picture there, which is really just a bit of revision. We did the same thing for capacitance, so we've done that now for inductance. Any questions at all about inductance and capacitance? We've looked at all 5 now. We've looked at their equations. We've looked at their characteristics, where they come from. And that final one about mutual inductance, I would really like to introduce this. But maybe I introduce it when the time comes, when we study these transmission lines affecting each other. Because what I'd like to do on Wednesday is do an example on the board, a calculation example that will help you with your assignment. Okay, thank you very much. I'll see you again on Wednesday.